Hey, it's Mr. Lum again, and this is your answer key for your practice quiz. Okay, here's question number one. It says calculate the maximum mass of magnesium hydroxide, which will dissolve in 120 mils of water. Okay, so first thing is, let me get my pen going here. Wrong one. No, this one. Okay. First thing is that we have magnesium hydroxide right here. This is the KSP of this thing. This is it right here. So magnesium hydroxide will dissolve into magnesium 2 plus 2 OH minuses. And this will dissolve in an X to 2X kind of manner. That means the KSP of this thing will equal magnesium times hydroxide squared, or in other words, 5.6 times 10 to the minus 12 equals X times 2X squared. Or instead of X times 2X squared, we can write just 4X cubed. Okay, do some math on this stuff, and it's going to be 5.6 times 10 to the minus 12 divided by 4. After you divide it by 4, you're going to take the cube root of it, and that's going to equal my X. So I have my calculator here. I'm going to go 5.6 times 10 to the minus 12 divided by 4 equals, and I take the cube root of it, and I get X equals 1.186 or 1.119 times 10 to the minus 4. Okay, and that is my molarity. Now the question isn't asking for the molarity of magnesium hydroxide. It's asking for the mass. And so since we have this, I'm going to have to convert my molarity into mass. So I'm going to take my 1.119 times 10 to the minus 4 moles over liters. I times that by my number of liters, which is 0.15 liters. I'm now into moles. I wanted to convert that into grams, so I'm going to times that by my molar mass. So my molar mass of magnesium is 24.3 plus 58.3 grams. Plug that into my calculator, 1.119 times 10 to the minus 4 times 0.15 times 58.3 equals 9.78. Question is going to be 2 sig figs because of KSP, so it's going to be 9.8 times 10 to the minus 4. And that's grams. So a very small amount. It is low soluble, that's why it's such a small amount of mass. Okay? So that's your answer number 1. I don't know why I have this is written like that. What is the concentration of fluoride in a solution of strontium fluoride? I have the KSP of strontium fluoride down here is 4.3 times 10 to the minus 9. So I am going to go strontium fluoride turns into strontium 2 plus 2 fluorides minus. This is going to dissolve in an X to 2X fashion. It says what's the concentration of fluoride? So it's going to be KSP is going to be, I should write it out. KSP equals strontium times fluoride squared. Or in other words, plug in my values. KSP is 4.3 times 10 to the minus 9 equals strontium, which is going to be X times 2X squared. X times 2X squared is the same as X times 2X times 2X. So 1 times 2 times 2 is 4. X times X times X is X cubed. Okay. So now I solve for X. And X is 4.3 times 10 to the minus 9 divided by 4 equals, and I take the cube root, trying to find my cube root button, that one, and I got 1.02 times 10 to the minus 3. That's my concentration of X, which will be the concentration of strontium fluoride, which will also be the concentration of strontium, but it is not the concentration of fluoride. Okay, so in order to get the concentration of fluoride, this number will be doubled. So 2.04. So because this is a 2x, you have to double it to get your fluoride concentration. So this value would be double that, so 2.04 times 10 to the minus 3 is the molarity. Now, sig figs, this should be 2 sig figs, so just be 2.0 times 10 to the minus 3 molarity. Okay, I guess I should write that in there. 2.0 times 10 to the minus 3 molarity. And that is my answer to number 2. Okay. Fix my computer. Okay. Oops. Okay. This next question. Again, I don't know why it did this thing of whatever, that kind of stuff, but formatting error. Which of the following will conduct electricity? This is a fancy way of saying which is an ion in water. Okay, this is alcohol. This is actually a bad formula for alcohol. This number right here is supposed to be a 2. CH3CH2OH. That's a typo, I guess. Anyways, this is alcohol. Supposed to be, if that was a 2, it's supposed to be an alcohol. But more importantly, that's covalent. This is the formula for a monosaccharide, or like a glucose or a fructose or something like that. But it's a basic sugar. But more importantly, again, you don't have to know if it's alcohol or sugar, it's covalent. Okay? NH4 is a positive, Cl minus is a negative. This is ionic. Okay? And this thing right here is covalent. Okay? So which one will which one will conduct electricity? Ions conduct electricity, C. Okay, So this next one is a little bit tricky. And we talked about it very briefly at the very beginning, and I think we kind of moved on. So I'd like to cover this one right here. If you look at all of these things, they are all soluble in water. Actually, like this one right here is covalent. So this is not the answer. It will not conduct electricity at all. So D is completely wrong. But for NaCl, this will produce Na+. It is ionic, so it will conduct electricity. But more importantly, it's also soluble. So when you have 1 molar NaCl, it'll produce 1 molar Na and 1 molar Cl. Okay? Soluble, it will actually conduct electricity very, very well. Okay? But now let's take a look at this one. Here is nickel 3 chloride, and it'll produce nickel and it'll produce chloride. But more importantly, it produces 3 chloride. So the next thing is nickel chloride is also very soluble. So this will produce 1.0 molar nickel and 3.0 molar chloride. This one has a higher concentration than the first one. So this one will conduct electricity more. Now MgCl2 will produce Mg2 plus and Cl minus, but it'll produce 2 of them. So when it dissolves, again, MgCl2 is very soluble. So it'll produce 1.0 molar, and this will produce a 2.0 molar solution. But not the concentrations of this one is actually the highest. And the more ions that are in solution, the more it'll conduct electricity. So this conducts electricity very good, the first one, but it only produces 1 molar and 1 molar concentrations. B produces a 1 molar and 3 molar concentration. C produces a 1 molar and 2 molar concentrations, and D doesn't produce ions, so it doesn't even produce anything. It doesn't conduct electricity at all. So the answer would be B in this case. Tricky one, but yeah. There's a lot of different answers for this one. A solution containing calcium, strontium, and silver. How do you separate these things? So calcium, strontium, silver. If you struggle with this stuff, I suggest making the table. If you are good at solving these questions, then you can get away with no table. But I do recommend a table for kind of everyone, to be honest. So I make my table. The first thing I'm looking for is remove one of these things. The first one I'm going to remove is silver, because I think it's nice and easy. And I can choose any one of these anions here, chlorine, bromine to this. So I'm going to add NaCl. Actually, let me see. I'm going to add Cl minus. No precipitate, no precipitate, precipitate. Okay, so essentially silver's been removed out of my thing. I'm now going to add some, I think hydroxide, OH minus, and that's going to form a precipitate. No precipitate. This forms a precipitate, but it's already out of solution. And then I can just add pretty much whatever I want, or I add carbonate. In real life, these are the things that I usually pick because they're cheap. Chloride is cheap, and same with hydroxide, and carbonate is quite accessible as well. Anyways, now you can't just get chloride off the shelf. So my first thing is step 1, add the spectator ion attached to the chloride, and that forms a precipitate of AgCl. AgCl, and then step 2, filter. Okay. Actually, I should probably just write it like this to save myself from room. Filter, AgCl, precipitate. Okay. Step 3, add sodium spectator hydroxide, and then 4, filter the calcium hydroxide, precipitate, and step 5, I'm going to add sodium carbonate, and then step 6, I would filter the strontium carbonate, carbonate, precipitate. This is my answer. This is my work. Here we have our next question right here, and it's a trial KSP kind of question. I have this thing that's a little bit annoying. It's a CI/VI kind of thing, and let's get my pen again. But I'm going to show you how to do the CI/VI thing really quickly, and then if certain things work out, you can like I'll show you a little trick in case when you do have equal volumes. It only works when you have equal volumes. Anyways, so I'm going to find my new concentration of PB. So I'm going to use my CI, which my original concentration of PB, NO3 is just a spectator. So my original concentration of PB is 1.0 times 10 to the minus 3. I times it by my VI, which is 0.1 molarity. 0.1 liters, sorry. Divided by my volume final. So after I add these two 100 mils, it's going to be 0.2 liters. So 1.0 times 10 to the minus 3 essentially divided by 2 is going to be your 0.5 times 10 to the minus 3 molarity. That's my cat. I'm just going to get him out of here. Okay. Is 0.5 times 10 to the minus 3. This is my new concentration of PB, by the way. Okay. Okay, same thing for this one. I don't even have to do a CI/VI. If you have equal volumes, and it only works for equal volumes, okay, then you can just take your concentration and essentially divide it by 2, because you're just doubling. You're doubling the volumes, so it's just going to be dividing it by 2. So anyways, again, Mg is a spectator, so SO4 2 minus concentration is just going to be 2.0 times 10 to the minus 3. I doubled the volume of water essentially, so 2.0 times 10 to the minus 3 now equals 1.0 times 10 to the minus 3 molarity. Okay, so now I have my new concentrations of PB and SO4. I'm just going to write a trial KSP equation. So it's going to be PB SO4. Let me fix that 4. Where's my erase button? Right here. Turns into PB2 plus plus SO4 2 minus. This is going to be 0.5 times 10 to the minus 3, and this is going to be 1.0 times 10 to the minus 3. And now we can kind of multiply these things together. And so when you get like things like this, you can kind of just like you can just like multiply the numbers together and just kind of go 1 times 0.5 is just simply 0.5 times 10 to the minus 3 times 10 to the minus 3 is just going to be times 10 to the minus 6. Okay, that's not exactly the best way to write scientific notation, so I'm just going to move my decimal place 1 over. So it's just going to be 5.0 times 10 to the minus 7. Now, this value that we just came up here is my trial KSP, sometimes known as Q or TIP, trial ion product. It's all the same thing, but this is this. Okay, now it happens to be that my trial KSP is larger than my KSP. Okay, which is right down there. And so that means we have too much PB and too much SO4. And since that is the case, that means a precipitate forms. Okay, and that's that. These are some provincial exam questions. I can't remember what exam I took it from, maybe the late 90s. In a saturated solution, you have potassium nitrate, and the rate of crystallization is, so saturated solution is a fancy way of saying equilibrium. And so that means the forward rate of reaction is equal to the reverse rate of reaction, or the rate of crystallization is equal to the rate of dissolving. Okay? In a experiment, 0.5 moles of FeNO3 is dissolved into 2 liters of water, and it's asking me the concentration. So for this one right here, I have 0.5 moles in 2 liters of water. Okay, and that means that equals 0.5 divided by 2 is 0.25 molarity. Now it's going to be 0.25 molarity is going to be the concentration of FeNO3 3. That's the concentration of that. I don't like that bracket. Okay, but FeNO3 3, when it ionizes, turns into Fe3 plus 3 NO3 minuses. That means this is a 1 to 1 to 3 ratio. So the this concentration will be 0.25. This concentration will be 0.25. This concentration will be 0.25 times 3. Uh, 0.75. Next question. A precipitation reaction occurs when equal volumes of 0.2 Pb and Ki are mixed. Potassium is a spectator. Nitrate is always a spectator, as well as potassium. It's always a spectator. So the only things that are going to be reacting is Pb and I. If you look at your table, Pb and I has low solubility. No, I is -1 and Pb is 2 plus. So the precipitation, the net ionic equation, net means get rid of your spectators, and that is it. Okay, it says it wants the precipitation reaction. Okay, so a precipitate forms. So this is showing the precipitate is forming. This one right here, some people may want to do it because they're used to like dissolving reactions. This is a dissolving reaction. It's a one-way. It's going from a solid and dissolving into its ions. This is a dissolving reaction. This is our precipitation or crystallization reaction. These are just bad answers. That's just all spectators and stuff like that. So there's your answer. Reagent, I don't know if I covered that. It just means like a reactant. It's synonymous. That may be used to separate Cl from S by precipitation is, okay, so I have Cl and I have S. This is just all this right here. This will work. Silver will take out chloride. Will silver take out this? So silver is part of all others and it's low soluble. So actually silver will not. It forms a precipitate with both. What about Pb? Pb is low soluble with chloride. Where is it? Pb is low soluble with chloride. Pb is also low soluble with sulfide. So not that one. And what about aluminum? So we have aluminum right here. Aluminum does not form a precipitate with chloride, but it does form a precipitate with sulfide. That's your answer. Okay. So if you were to make a table of this one right here, like Cl and S2 minus, what do we got here? How it would look is like this. No precipitate, no precipitate. Precipitate, precipitate. Pb, precipitate, precipitate. No precipitate, precipitate. This is the only one right here that has different things. Okay, so that's your answer. Next question. At a certain temperature, the solubility of BaF2 is this. What's the KSP of this thing right here? So BaF2 will dissolve and turn into Ba2 plus 2F minuses. It's moles per liter. So if this is 7.4 times 10 to the minus 3, this is also 7.4 times 10 to the minus 3. And that means this one's going to be 7.4 times 2 is 14.8 times 10 to the minus 3. Okay, or 1.48 times 10 to the minus 2. Now, so now we have this thing right here. I'm just going to write my KSP expression. My KSP for this thing is going to be barium times fluoride squared. Okay, plug in my values. KSP, sorry, we're just going to write over here. KSP is 7.4 times 10 to the minus 3 and 14.8 times 10 to the minus 3. What did I forget? Squared. I say that a lot. Like, what did I forget? Because I always see people forget that stuff on tests. They always drop their squares. So please get in the habit of trying to catch that stuff. Do that on my calculator. 7.4 times 10 to the minus 3 times, oops, wait, times 7.4 10 to the minus 3 equals 1.6 1.62 times 10 to the minus 6. And so that's my answer. Just rounding to 2 sig figs, because this guy has 2 sig figs. This guy has 2 sig figs. Okay. What is the maximum amount of strontium that can exist with 0.1 sulfate? So you have a solution of this thing right here. 0.1 molar sulfate, like that, and it's asking what is that. Like I very quickly just got rid of my spectator, but I want to remember is that, like, if this was like some other type of different spectator, it could hypothetically change the concentration of SO4. Like sometimes, like let's imagine it was some crazy spectator that looked like I don't know, we'll just say spectator X, and then it had SO4 and then a 2 on the outside. That means if this was 0.1 molar whatever X is SO4 2, that means the SO4 concentration would be 0.2 molar. Okay, so just be aware, like, it's okay to get rid of your spectators, that's what you're supposed to do, but they can affect your concentrations of some of your anions or cations or something like that. Anyways, this one doesn't though, because there is no 2 on the outside of SO4, so it'll just be 0.1 molar. Anyways, KSP equals the concentration of SR2 plus times my concentration of SO4 2 minus. These are just 1-to-1, so there's no squares or anything like that. Strontium sulfate is 3.4. Plug in my values. 3.4 times 10 to the minus 7. And that equals X times 0.1. So we don't even need a calculator to solve this kind of stuff. 0.1 divided by both sides is going to be 3.4 times 10 to the minus 6. And yeah, and that's our answer. Okay. Hopefully you feel ready for the Unit 3 quiz and tests.